Hello everyone, I will be doing 5.36 from Griffith's Intro to Electrodynamics. This problem asks to find the exact magnetic field a distance z above the center of a square loop side of W carrying a current I. Verify that it reduces to the field of a dipole with the appropriate dipole moment when z is a lot greater than W. So first we're going to find this exact magnetic field, a distance z above the center of this square loop. So we know that the sides are W, and we're trying to find the magnetic field at this point above this square loop. So we can try to find it at this point, that is this distance from the square loop. We can call this distance S, and we know that this side is W over 2, as well as this side is also W over 2, and where this is distance Z above this square loop. And we can solve for S quickly here to be the square root of Z squared plus W squared over 4. And we can find the magnitude of the magnetic field from one side of this square loop from example 5.5. And from equation 5.37, we're given that the magnitude of the magnetic field is equal to mu naught I over 4 pi S times sine theta 2 minus sine theta 1. And these theta 2 and this theta 1 are essentially the boundaries to the distance that we're trying to find here. It was a lot less. This is supposed to be linear, but where this angle is going to be theta 2 and this angle is going to be theta 1, and we can find the sine theta 2 for this side of the square loop to be W over 2 over the square root of S squared plus W squared over 4, just using Pythagorean theorem, and this will give us W over 2 over Z squared plus W squared over 2 of the square root. And similarly, for sine theta 1, this is going to be the opposite, so it's going to be negative, and we will have the same expression for sine theta 1. With the negative, of course. Now that we have this distance S from this long wire here that we're approximating from this example 5.5, we can find the magnitude of this magnetic field from this side of the square loop. To be mu naught I over 4 pi times this S, which would be 1 over Z squared, or the S value is rather the square root of Z squared plus W squared over 4 times sine theta 2 minus sine theta 1. Minus and a negative, make a positive. u squared over 4 times w. This 2 is going to cancel out when we add them together. So we don't need these parentheses anymore. Square root of z squared plus w squared over 2. And that's going to be the magnitude of our magnetic field from this one from this one wire segment of the square loop. Now, this doesn't give us a direction, so one way that we could find our direction is from first looking at it from a side view this time, looking at it from the x and z plane, where this dot is going to be representative of this wire coming out of the plane, or out of the page rather, and we're finding the magnetic field from this distance right here. So this is our S value, and this is our Z. This is our Z hat direction, this is our X hat direction. This is W over 2, because it's W over 2 distance. And from example 5.5, we know that it would be coming out of it would be perpendicular to the plane from which we found it from. So our magnetic field is going to look something like this, where it's perpendicular to this plane from the distance of the wire. And if we find this angle, let's call it phi, if we find this angle, then we can find the direction, we can find the magnetic field in the z hat direction. And we want to find it in the z hat direction because when we add up all of the magnetic fields from all of the sides, they're going to be pointing in every one of these directions, and these x and y terms are going to cancel out with each other, leaving only this z hat direction for the magnetic field. So we can find that by multiplying by this sine phi. We can get this sine phi from using geometry. We know that this phi angle would also be the same here, which means that sine of phi would be w over 2 over the square root of s squared plus w squared over 4 equal to w over 2 I'm just over the square root of z squared plus w squared over 2. Now if we multiply this into our expression, then we can find the z hat direction of the magnetic field. Again, multiplying our sine phi here. Z squared plus w squared over 2, the square root. The square root of z squared plus w squared over 4. This 4 is going to become an 8 because of this w over 2. This is going to be a w squared, and these two are going to multiply together to give z squared plus w squared over 2, no longer in a square root. And finally, we know that this is only one segment. So if we multiply it by all 4 segments of this square loop, then we can find this magnetic field to be mu naught I over 2 pi times 1 over square root of z squared plus w squared over 4 times w squared over z squared plus w squared over 2. I believe I made a mistake somewhere. This should be a 2. Oh, this should be, I missed this 4 here, because this is actually z squared, rather. Yeah, that's my bad. So this should be 4. And multiplying that in, just fix this mistake real quick. This should be z squared plus w squared over 4. And this would be the square root of z squared plus w squared over 2. Okay. And that's in the z-hat direction, and that is our magnetic field above this square loop from all segments, from the entire square loop. The second part of this problem asks to verify that it reduces to the field of a dipole for the appropriate dipole moment when z is a lot greater than w. So for z greater than w, we know that the B field would be equal to mu naught I w squared 2 pi. One term here will reduce to a z, and the other term will reduce to a z squared. Mu naught I times w squared over 2 pi z cubed in the z-hat direction. So now I want to verify we want to verify that it reduces to the field of a dipole. So we can find the dipole moment as the current times the area. So I squared, IW squared in the z-hat direction. And there is a current here. Going either direction, but there's a current from the square loop times the area of this square loop in the z-hat direction, giving us our dipole moment. And from equation 5.88, we can find the magnetic field of this dipole to be mu naught m over 4 pi r cubed times 2 cosine theta r hat plus sine theta theta hat, where theta is this polar angle. So since we're trying to find it in this z-hat direction, it's going to be equal to 0, and this r vector is going to be in the z direction with a z magnitude. So we can substitute these in, as well as this dipole moment, mu naught I w squared over 4 pi z cubed. Substituting our cosine of 0 is just 1, and sine of 0 is just 0, so 2 r hat. And we can write this as mu naught I w squared over 4 pi z cubed, where this 2 and 4 cancel each other in the z hat direction, because the r hat is the same as the z hat direction. And this is the exact same value that we got for our B field, which verifies our solution. Thank you.